So you have seen that you have two sources of angular momentum, spin angular momentum and orbital angular momentum, and they are behave as a magnetic dipole when placed in a magnetic field. They are produces there is an interaction between the external magnetic field and these dipoles. This changes the potential energy, and this potential energy term is added into the hydrogen atom Hamiltonian. This we did in the last module. Okay. Then I said you that if you have two different sources of angular momentum, then they could be added up to give you the resultant angular momentum, and the symbol given to the resultant angular momentum was J. And I said you that all the operator algebra which we talked about in case of angular momentum, commutation relationships, all this will be valid in the for the resultant angular momentum also. Okay, so if you have one orbital angular momentum and another spin angular momentum, then they could interact with each other and they can change the energy state of the system. So this change in the energy state is normally represented in terms of a spectroscopic term symbol. And for a multi-electron atom, you have different source of orbital angular momentum and different source of electron angular moment, spin angular momentum. Okay. Now these different sources of orbital angular momentum and spin angular momentum can be summed together. So the total orbital angular momentum is denoted by a capital L symbol, and it is simply summation of all Li. Same way, total resultant spin angular momentum is summation of all Si, and it is given as the total spin angular momentum is given as capital S. So now, since we are talking about multi-electron atom, so we will be more interested in capital L and capital S. Whenever you calculate this capital L value, then corresponding to each of these, this will be an integer, and corresponding to each integer, there will be a spectroscopic symbol. This SPDF, which is called, is actually a spectroscopic symbol. Okay. And whenever you have these sources, then once you have the total orbital angular momentum, total spin angular momentum, then they also may be combined together to give you a total angular momentum called J. J is the total angular momentum, including a spin, including orbit. Okay. Now, if you find the before we find the spectroscopic term, let me tell you that any closed shell like structures, means if you have S2, 1s2 configuration, that will be for the helium atom ground state, then you have, it can be accommodate only 2 electrons. Okay, and if it can accommodate only 2 electrons, then what is the L? A small l for S is 0. Okay, and what is the spin? The spin is paired, so the total spin is also 0, and total L, if I say capital L, then capital L is 0 plus 0, because both electrons have 0 azimuthal quantum number, and capital S is also plus half, sorry, it's plus half and minus half, so this is also 0. So for capital L, you have the symbol, with a spectroscopic symbol is S. Okay, now this, so for this configuration, the spectroscopic term which you can write is capital S, and then as a superscript, what you will write? As a superscript, you will write 2s plus 1, and capital S is 0, so 2s plus 1 will be equal to singlet S. Singlet S will be the term for this particular configuration. So we say that because all the electrons are paired, same will be the term for S2, for P6, for D10. Okay, for S2, P6 and D10. So always they will have a term like 1s naught. Okay, because L is equal to 0 and S is equal to 0. Okay, and L is 0, S is 0, so J is also 0. So 0 you can put as subscript. So 2s plus 1 Lj will, for any closed subshell like structures will be like this one. So this you remember. Then another common feature of the spectroscopic term is that if you have a configuration like D2 and D8, altogether 10 electrons could be in the d orbital, because you have 5 different kinds of d orbitals. So if you have 2 electrons only, then you have 2 vacancy here. Both these will give you the same spectroscopic term. Same way, D1 and D9 will give you the same spectroscopic term. Same way, D3 and D6 will give you the same spectroscopic term. Okay? Sorry, D3 and D7. D3 and D7 will give you the same spectroscopic term. So that's what is written, that if NLX and that of NL R minus X, X is 2 and R is the maximum number of electrons. So 10 minus 2 will be 8. So D2, D8. I have written here. D2, D8, D3, D7. Same way for L is equal to 1, P1, P5, P2, P4 will give you the same term. So if you find the term for the P2, you can apply it for the P4 also. If you found the term for D2, then you can apply it for D8 also. And these term symbols are, I'm saying, very important in coordination chemistry. If you will do a course, it will be a repetition there. But here what we are doing is that you know the source of the spectroscopic term, because it comes from the addition of angular momentum. Okay. So once we have these, then we say that the total number of state which is possible for a particular configuration, say P2 configuration I have started with, is given as 2n factorial divided by r factorial into 2n minus r factorial for equivalent orbitals. Okay, so this is very important. Equivalent orbital means if you are talking about P2 configuration, then you have both the electron in the same PE, like this one. One of the configuration is this one. It can change. You can change this configuration, or another configuration you can write for P2 is like this one. Nobody stops you from writing this one. You will say that you have not done it, but it's equally probable that the electron could be like this one. The energy could be different. So one of the excited state configuration could be this one. This will be the ground state configuration, but this could be excited state configuration. Okay, because energy will be different. So all these states which is possible are called microstate. All different kinds of configurations which is possible. And these microstates, and for the equivalent orbital means in the same. If you have, I just gave you an example of 1s2 helium atom. If I excite this electron, one of the electron, 1s2, and it goes to 2s1, then now it is one electron only here. These two electrons, 1 and 1, are in different orbitals. It could be you have 1s2, 2s2 and 2p2. Okay. So this is the carbon atom. If you have like configuration like this one, s1 and p1, one electron in s orbital and another electron in p orbital, then they are non-equivalent electrons. We will talk about this later on, but first we are talking about equivalent electrons. Okay. So if you have equivalent orbitals, then the total number of microstate is given by this one, and where this n is equal to 3 for p orbital and n is equal to 5 for d orbital. Means if you don't remember, just remember that number of the boxes which you draw in the orbital is given by n. Okay, and then r is the number of electron which is present. So for P2 configuration, n is equal to 3 because 3 boxes you drive, and r is equal to 2. So if you calculate the number of microstate, then total number of microstate which you get is 15 for a P2 configuration. Okay? All different kinds of configurations you will have to take into account. And if I give you this value, then when I say all different kinds of configuration means, what does this represents? This particular configuration represents that you have, sorry, this is a p orbital. So we should be done. I cannot draw here. Let me draw here. These are p orbital. Okay. So you say +1, 0, and -1 for the time being. That's what you have written. Okay. So if I say the 2 electrons which is present is like this one, it's not possible. Okay. In the same box, you do not draw the same spin, +half and +half. So it is omitted. First, it's all different kinds of configuration is written, and then everything is omitted. See, this represents one particular configuration for the 2 electrons. This represents one particular configuration. This represents one configuration, and this represents another configurations. Okay. So this 1 plus stands for ML1 is equal to 1 and MS1 is equal to +half. And 1 minus stands for ML2 is equal to -half and MS2 is equal to -half. Okay. So these symbols are given, and thereafter all these configurations which is crossed is not feasible by Pauling's principle. Okay. What does it remains which is not crossed? You see 1, 2, 3 here, then you have 4, 5, 6, 7, 8, 9, then you have 10, 11, 12, 13, 14, and 15. So 15 microstates are drawn here. Okay, and in this table. This table is from Quantum Chemistry by Mercury, 2nd edition. Okay, so you can see there this table. Now, once you have this table, then it is very easy to write the term symbol for hydrogen atom. Okay, and what does it mean? That in this table, what you find out, what is the largest value of ml value? So the largest value of ml is 2. And in this row, the first row of ml is equal to 2, you find only one microstate, that is 4th microstate I have given symbol. Okay, which has ms is equal to 0. And for this, the corresponding ms is 0. So what we say, the largest value of ml is 2, which occurs with ms is equal to 0. So if ml is equal to 2, then capital L is equal to 2 and s is equal to 0, and this will be singlet D term. I said in the earlier table. So capital L is equal to 2 means D symbol, and s is equal to 0 means spin multiplicity 2s plus 1 will be equal to 1. So it is 1, singlet D. This we say as the name which you will call is singlet D. This you get. Now for L is equal to 2, ml can have 5 different values, +2, +1, 0, -1, -2. So the number of microstate which will account for this singlet D should be 5. Okay. In each will account for one microstate in each row of the middle column. So we say 5 different states will account for singlet D. Now, if 5 different states will account for singlet D, then this alone will not be sufficient. So what we say is that from this ms is equal to 0, because it's singlet, so it has to be from this column only, from the middle column only, 5 different states. So one of these 4 goes, no issue. We say that from each row in the middle column, one of the one of this will be assigned to singlet D configuration. So this is singlet D, fine, no issue. If one has to go, here also you have single, so this is also account for singlet D, 12th also, no issue. But in the rest of the row, you have more than one microstate. So which microstate you should choose? That's a question. And we say arbitrarily you can change any one, that will not affect. Okay. So arbitrarily you choose this one, arbitrarily you choose this one, and arbitrarily you choose this one. Okay. So all these 5. Let me see if I can change the color. See, this is singlet D, this is singlet D, this is singlet D, this is singlet D, this is singlet D. 1, 2, 3, 4, 5. And this is arbitrary selection. In between the 3, you could have chosen this one also, you could have chosen this one also. But arbitrarily we choose these 5. And so what will happen? Now one of the spectroscopic term you have written singlet D. So you will omit all the terms which you have accounted for, and you will make a new table with a similar table, ML and MS table. So that new table will contain, in the first row, no microstate, in the last row, no microstate, in the middle column, 5 of this will go, okay, and you will see that in the first and second column, the 13, 14, 15 and 1, 2, 3 will remain there. So let's see what do you get. So the new table is like this one, eliminating all the microstates which is not feasible because of polling method, and which we have accounted for singlet D. Now we can write a new table. Again, this is from quantum chemistry by Macurie. So if you use this one, you see first row no term, second row no term. In this there was term, so we deleted from each of these row one term we deleted for singlet D. Now you have this one. For this again you find out what is the largest value of the ML. So the largest value of ML which is here is 1. Okay. And if it is 1, then you have MS value 1, +1, 0 and -1, all 3. So the largest value of MS is also 1. So you will take largest value of ML, largest value of MS, and corresponding to 1 the spectroscopic symbol is P. So P you will take, and if S is equal to 1, 2S plus 1 will be 3. So the term will be triplet P. You see the largest value of ML is +1, which occurs with MS equal to +1, 0, -1, and this accounts for 9 microstate corresponding to L is equal to 1, S is equal to 1, and the term is triplet P. Now it accounts for 9 microstates. Okay. So what is how do we choose these 9 microstates? These 9 microstates you can choose this one, this one, this one. It's all single, so no issue, it will go. Here you have 2 different terms. So obviously you will choose this one and you will leave this one. So what remains is, in this table, what remains is this one. Only single term with ML is equal to 0 and with MS is equal to 0. So if ML is equal to 0, MS is equal to 0, the term will be singlet S. Okay, and we have accounted for all the microstates. So the next term will be singlet S, microstate. Okay. So we have 3 different terms: singlet D, triplet P, and singlet S. As far as J value is concerned, now you can write for singlet D term, L is equal to 2 and S is equal to 0. So J value will be 2. And the term symbol is singlet D2 and its degeneracy is 2J plus 1, 5. So the degeneracy of the orbital, I said you 9 different terms is given by 2J plus 1 values. Okay. For triplet P terms, you have L is equal to 1 and S is equal to 1. So Mj will be again 5. So J will be equal to 2. and mj will be plus 1, 0, minus 1 and j is equal to 1. So, and again mj is equal to 0, j is equal to 1. So you see, for this term, I have divided the mj into 3 different categories. Okay. One is plus 2, plus 1, 0, minus 1, minus 2. Another is plus 1, 0, minus 1. And third is mj is equal to 0. And each of these will have a different j value. It means the triplet P term will not remain same, will not give you one single spectroscopic symbol or a Wilson-Dot term symbol. It will give you 3 different for this one. So it will be triplet P2 for this one, triplet P2, and 2j plus 1 will be 5. So 5 macrostate will be accounted by this one. Then it will be triplet P1 for this one, and 2j plus 1 will be 3. So 3 terms will be accounted for from this state. Okay, 3 terms. Sorry, and then you have triplet P0, which will account for 1 term. So 3 plus 1, 4 plus 5, 9 different terms. Okay. So all these, for the remaining 1 microstate, L is equal to 0 and S is equal to 0, J is also 0, so singlet as 0. So if you write the full term, then you have, for that P2 configuration, you have singlet D 2, singlet D 2, then you have triplet P 2, then you have triplet P 1, then you have triplet P 0, then you have singlet S 0. So all these are spectroscopic term symbol for P2 configuration. And for the reasons which I said you earlier, this will be the term for the P4 configuration also, because P2 we have done. Same, this is one way of finding out the spectroscopic term symbol. Okay, you can find out. I will tell you a more logical, another logical way, not more, another logical way of finding out the spectroscopic term symbol, and I have taken D2 as an example, D2 configuration, which you get in quantum chemistry. Okay, D2 system. The moment you go for D, you talk about transition metals, and so it's more applied in the coordination chemistry. Okay, so for D2 system, what is happening? For D2 system, the maximum value of the ml is plus 4. Okay, because if you have a D, this is your d orbital. Okay, and if both the electrons occupy in the first box, then the maximum value of the ml value you get, and it's plus 4 for the 2 electrons. Okay, so ml value could be plus 4, plus minus 4, plus minus 3, plus minus 2, plus minus 1 and 0. Okay. Now what we will look for, that for finding out the macrostates, if you calculate for the D2 system the number of macrostates, it will come out to be 45. That you will find out it will be 45. So if you do this calculation for each of these ml values, you find out the different configurations which is possible. So how many arrangements are possible for obtaining ml is equal to plus minus 4? I am writing both plus and minus. So one of the configuration will give you plus 4, and on the right left hand side, on the right hand side it will give you minus 4. Okay, and what we write is, as a conclusion, that ml is equal to plus minus 4 occurs 1 time each, means plus 1 time and minus 1 time. So 1 time each, plus minus 4 occurs, and both have 0, so ms equal to 0 occurs 2 times, not each, because it occurs only 2 times. Here also ms is 0, here also ms is 0, because it's a paired spin. Same way, exactly like this one, we will find out ml is equal to plus minus 3, ml is equal to plus minus 2, ml is equal to plus minus 1, and ml is equal to 0. What are the ways in which it is present? Look at this one. ml is equal to plus minus 3. Now you see, it's all in the plus 2 and plus 1 electron on the left hand side. So only the spin is changing. Both plus half spin, then plus half minus half spin, then minus half plus half spin, then minus half spin. So these all four configurations on the left hand side will give you +3, and all four configurations on the right hand side will give you -3, because they are filling in the -2 and -1 boxes. Okay. So again, only the spin is changing here also, and what do you find? The result we find is that ml is equal to ±3 occurs 4 times each, and ms is different now. ms is equal to ±1 occurs 2 times each, and ms is equal to 0 occurs 4 times. So altogether 2 times each means 4 times, okay, and ms is equal to 0 occurs 4 times, so 4 plus 4, 8 configuration. It is the ms we have written, and 4 times each, so this is also telling you 8 configurations. So this was about ±3. If you go for ±2, then you have this type of arrangement. It could be in +2 and 0, okay. It could be +2 0, +2 0, +2 0, so +2 configuration. Then you have -2 0, -2 0, -2 0, and you have these configurations, okay. And I think this is this also gives you, okay, out of these 4, this also gives you -2, this also gives you +2, because both the electrons are paired here. And if you count their spin, then what you can write is ml is equal to ±2 occurs 5 times each, and ms is equal to ±1 occurs 2 times each, and ms is equal to 0 occurs 6 times each. So altogether you have 1, 2, 3, 4, 5, so 10 configurations, and 2 times occurs 2 times each means 4, and 6, so 4 and 6, 10. It accounts for 10, and 5 times each means it also accounts for 10. So these are the results for these configurations. Then go for ml is equal to ±1, and you obtain this one. ml ±1 occurs 8 times each, and ms is equal to ±1 occurs 4 times, and ms is equal to 0. Sorry, this should be 0, occurs 6 times each. So 4 times means it is total 8 times. So 1, 2, 3, 4, 5, 6, 7, 8. So total 16 terms should be there, okay. And this occurs, ms equal to 0 occurs 8 times, I think 8 times. 8 times, and this occurs 4 times. Let me check. ms is equal to 8 times each, and ml is equal to, sorry. So you see ±4 1 time each, and ms is equal to ±0. Its total is counted here, okay. Anyway, I've counted the total figure, but it accounts for 8 times each, means it's 16 configurations. So ±1 occurs 4 times each, means 8 configuration here, okay, fine. 8 configuration here, and this also occurs 8 times, I think, 8 times, okay. So make the correction, you just count ms value, and you will get the 0 value 8 times, okay. So the total of ms you will count, and you will get 0 value. So 4 times each, it will be each. Make these corrections, so it will be 16, okay. So this will give you. Now for 0 configuration, you have these configurations, okay. So one of the 0 could be like this one, that both the electrons are paired in 0 box, and or in +2 -2 or +1 -1. So what do you get? ml 0 occurs 9 times. So 4, 4 and 1, 9 times, not each. ms +-1 occurs 2 times each, so 4, and ms equal to 0 occurs 5 times, so 4 plus 5 is 9, okay. So this, and if you summarize these into a table, then this is what you get. For ml, the number of occurrence is given 1 time each, 4 time each, 5 time each, 8 times each, and 9 times only. ml is equal to 0. For ms, you get ±10 times each, and 0, 25 times only. If you summarize, if you sum all these together. So what do you get? The total state what you get is 45 here. And what do you get here? 8 plus 2, 10, 10, 20, and 20 and 36, 36 plus 9. So this you sum it up, this also will be 45. So we have counted for the 45 microstates in this table. Now if you go for writing ml and ms value, then you see this was the table, plus minus 4, the number I have omitted only, total number, plus minus 3, plus minus 2, plus minus 0, and this was our original table. Now what you go? You go for the highest value of ml and write the term for that. The highest value of ml is 4. So for 0, 1, 2, 3, 4, I have written S, P, D, F and G. So it will denote G symbol, and since it is one time only, so it will be singlet G. That's what is the logic of this logical method. Okay. How do you write the term symbol? Now once you have written it for the highest value of ml value, then you will omit this line, this row from the table. And now subtracting orbital multiplicity. So what is the orbital multiplicity? If L is equal to 4, then our orbital multiplicity is 2L plus 1. So 9 is the orbital multiplicity. So this 9 value will be subtracted from ms is equal to 0 and spin multiplicity from each ml values, and removing ml is equal to plus minus 4 row, a new table is generated. Okay. So now subtracting orbital multiplicity, which is 9 for G, from ms is equal to 0, and spin multiplicity is 1 from each ml value. So what you do for writing the new table, you will subtract 9 orbital multiplicity from ms is equal to 0. This will be minus 9, and from each of these you will do minus 1, minus 1, minus 1 and minus 1. And you will omit this one, this row, because for plus 4 you have already written it. So the new table will be ml is equal to plus minus 3, it will be 3 times. You see, 4 minus 1 is 3. So you should get what? 3, 4, 7 and 8. So what you get? 3, 4, 7 and 8 for 3 plus 2 and plus 1. And from 25, 9 is omitted, so 16 you get. Okay. So this new table you got. Now here again do the same thing. From this table, highest ml value and corresponding term you write. Highest ml value is 3, so it will be, symbol will be F, and it is 3 times each, so it will be triplet F. Okay. And now orbital multiplicity is 12 plus 1, so 2 multiplied by 3 plus 1 is 7. So that 7 you deduct from this occurrence ms, and 3 and from this ml value you have 3 spin multiplicity, so you deduct this one ms value and spin multiplicity 3 from each ml values. So if you deduct 3 from each ml value, what do you get? This is what you get. ml is equal to plus minus 2. It was 4, so it became 1. Okay. It was 7, so it became 4. It was 8, it became 5. 3 you have deducted. And from this you have deducted 7. So 7 has gone from this one, 7 has gone from this one. It was 16, it was 10, so it is 3 and 9. Now from this value, highest orbital angular momentum, ml value is plus 2. So this will be D, and it is one time only, so it will be singlet D. Okay. It will be singlet D. Now again subtracting orbital multiplicity, which is 5. D means ml is equal to 2, also 2L plus 1 is 5, orbital multiplicity, and this you deduct from ms is equal to 0 value, and spin multiplicity, which is 1 from each ml value. So and remove this line. Okay. What does it mean? Remove this line, and then you get this one. ml is equal to plus minus 1 is 3 times each. Okay. Sorry. So it will be 3 times each, it will be 4 times each. 3 times each and 4 times only. And then ms is equal to plus minus 1 will be 3 times each and 4 times only. So again you keep on refreshing the tables and you will get the new terms. So here the highest value is plus 1 and it is 3 times each. So the term will be triplet P. And for triplet P, the multiplicity is, orbital multiplicity is 12 plus 1. So it will be 3. So you deduct 3 from this one, 3 from this one, and you will get only one term. Okay. And you will deduct 3 from here. It is triplet P, so 2s plus 1 is 3. This also you will deduct, and the only remaining term, which will be for ml is equal to 0 one time only, or for ms is equal to 0 one time only. And for one time only, ml is equal to 0 is singlet S. So altogether, if you look at this creation of occurrence and analyzing all the microstate, you got singlet G, triplet F, singlet D, triplet P and singlet S term for D2 configuration. Now, the rule is that terms having maximum spin multiplicity lies lowest. So, spin multiplicity is highest for triplet F, so it will be lie lowest. If the term have spin multiplicity, same spin multiplicity, then highest ML value lies lowest. So, highest ML value will be for F. They have the same multiplicity, but highest ML value is for F. So, F will be here, P will be here. Again, you have all spin multiplicity same, singlet, 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 singlet. So, highest ML value is for G, then D, then S. So, this will be the energy level of the different spectroscopic terms of the D2 configuration of a free ion term. Okay. So, this way, now again J value I have not written here, but if you write the J value, this comes out to be like this one. LS coupling scheme for D2 system gives you triplet F at the bottom, then triplet P, then singlet G, then singlet D, then singlet. And if you write the J value, then triplet F splits into triplet F2, triplet F3, triplet F4. Triplet P splits into triplet P0, triplet P1, triplet P2. Singlet G becomes singlet G4, singlet D becomes singlet D2, and singlet S becomes singlet S0. And the number of microstates it will account for, you see that is written in bracket, it will account for 1 microstate, it will account for 5 microstate, it will account for 9 microstate, then 5, then 3, then 1, then 9, then 7, then 5. If you sum it up, all should give you 45. So 7 plus 5 is 12, 12 plus 9 is 21, 22, 25, then 30, then 39, 140 and 45. So 45 microstates are accounted for in a D2 configuration by different spectroscopic terms. And all this concept arises because of L and S orbital angular momentum and spin angular momentum. Okay. Now, if you have the, I'm sorry, it's going to be a little longer, but don't worry. Just non-equivalent terms, a very small example I have given you here. Okay. Again, this is given in the quantum chemistry book by Donald McCurry. So, if you have 1s1 and 2s1, the only possible microstates are these 4 microstates. Okay. 2s spin up, 1s spin up and down, and then 2s spin down. Okay. And for this 4 different states, you can write these four different macrostates. Which, since now we have done all those calculations, so now it's easy for you to understand. So the only possible value of ML is 0, and it is maximum. It's maximum possible value also, and MS is equal to +1, 0, and -1. It's all possible. Okay. So since largest possible value of ML is 0, the corresponding value of S is equal to 1. Okay, and so the term is triplet S, which will account for 3 microstate. Okay. Now see. 3 microstate means S is equal to 1, so it will be L is equal to 0, here ML is equal to 0 and MS is equal to 0. Okay, so it will give you 3 microstates. So this will go, and this will go. Any one of this will go. So what will remain is 0 and 0. And so the other term will be singlet S. I did earlier for P2 case. So you have 2 terms, triplet S terms and singlet S term for non-equivalent electron of helium atom if it is excited to 2s1. So it becomes 1s1 and 2s1. Then you can write it like this one. So these are the ways by which you can find out the spectroscopic term. So we have done enough in the angular momentum chapter. And angular momentum, we will start new concepts in the next module. Okay, thank you.